The Early Universe and the Birth of Galaxies, a tale of gravity and dark matter. This is the story of how everything you see in the night sky came to be. And it all started with something you cannot see at all. Think about this for a moment. Every star you have ever looked at, every galaxy in every picture from the most powerful telescopes, every bit of matter that makes up your body right now, all of it was once packed into a space smaller than a single atom. And then, in less than a blink of an eye, it all changed. We call that moment the Big Bang. But here's the thing most people get wrong. It was not an explosion like a bomb going off in empty space. There was no empty space. There was no outside to look in from. The Big Bang was the beginning of space itself. It was the beginning of time itself. Everything that exists, including the room you are sitting in right now, was created in that moment. But here's what makes this story even stranger. The universe you see when you look up at night is only a tiny piece of what is really out there. Most of the universe is made of something we have never seen, something we cannot touch, something that does not glow or reflect light. We call it dark matter. And without it, you would not be here. The Earth would not be here. No star or galaxy would exist at all. This is the story of how gravity and dark matter work together to build everything. It is a story that stretches over billions of years. It begins in a time when the universe was so hot that atoms could not even form. And it ends with the beautiful spiral galaxies and the giant clusters of stars that fill the sky today. So let us go back, all the way back, to the very first moments after everything began. The universe was born hot. Unbelievably hot. In the first tiny fraction of a second after the Big Bang, the temperature was so extreme that our brains cannot really picture it. We are talking about numbers with dozens of zeros. Hotter than the center of any star. Hotter than anything that exists today. At that moment, there was no matter as we know it. No atoms, no particles that would look familiar to us. The universe was a sea of pure energy. It was a soup of strange particles that winked in and out of existence. Everything was packed so tight and moving so fast that nothing stable could form. But then something remarkable happened. The universe started to grow. And as it grew, it cooled down. Think of it like letting steam out of a pressure cooker. When things spread out, they lose heat. And when the universe lost heat, amazing things became possible. Within the first second, yes, the first second, particles started to take shape. The building blocks of everything we know began to appear. Quarks, the tiny pieces that make up protons and neutrons, started to stick together. It was like the universe was a factory running at full speed, making the raw materials for everything that would come later. By the time 3 minutes had passed, something truly important had happened. The universe had cooled enough for the first atomic nuclei to form. This moment is called nucleosynthesis. It is a long word that simply means the birth of atomic centers. Here is what formed in those first few minutes. Hydrogen nuclei, which are just single protons. Helium nuclei, which are 2 protons and 2 neutrons stuck together. And tiny traces of a few other light elements. That is it. Just hydrogen and helium, with hydrogen making up about 3/4 of everything and helium making up most of the rest. This might not sound exciting, but think about what this means. In just 3 minutes, the universe had created the fuel for every star that would ever shine. It had made the raw material for every galaxy that would ever form. The same hydrogen that filled the early universe is the same hydrogen that sits in your glass of water right now. But we are not done with the early days yet. The universe was still incredibly hot. It was still a dense fog of particles and energy. Light could not travel freely. If you could somehow be there and somehow survive, you would not be able to see anything. The whole universe was like the inside of a star, glowing but opaque. Light would bounce off particles and scatter in every direction, never traveling far before hitting something else. This state lasted for a long time, about 380,000 years. That might sound like forever, but remember, the universe is now about 14 billion years old. So this early period was just a brief moment in the grand timeline. Then came one of the most important events in the history of everything. We call it recombination. And despite the name, it was actually the first time atoms combined. not a recombination of anything that had combined before. Scientists just picked an odd name for it. Here is what happened. The universe finally cooled enough for electrons to settle down and join with nuclei. Before this moment, electrons were flying around loose, bouncing off everything. They scattered light like fog scatters headlights. But when the temperature dropped to about 3,000 degrees, electrons could finally stick to hydrogen and helium nuclei. Neutral atoms formed for the first time. And then suddenly, the universe became clear. Light could travel freely. The fog lifted. If you could have been floating in space at that exact moment, you would have seen the whole universe shift from a blinding glow to darkness. Because once atoms formed, there was nothing to make new light. The universe had cooled too much for the kind of glow that filled the early days. This transition left behind something amazing, a faint glow that still fills all of space today. We call it the cosmic microwave background, or CMB for short. It is the oldest light in the universe. It has been traveling through space for almost 14 billion years. And we can still detect it with special instruments. The CMB is like a baby picture of the universe. It shows us what things looked like just a few 100,000 years after the Big Bang. And here is what is incredible about it. When scientists first measured the CMB, they found something surprising. It is almost perfectly smooth. The temperature is nearly the same in every direction. Almost, but not quite. There are tiny differences. Spots that are just a little bit warmer or cooler than the average. These differences are incredibly small. We are talking about variations of 1 part in 100,000. That is like measuring the height of a mountain and being accurate to the width of a human hair. But those tiny differences are the most important thing in the story of how galaxies formed. Those little bumps and dips in temperature tell us that the early universe was not perfectly uniform. There were places where matter was just a tiny bit denser than other places, and those slightly denser spots would become the seeds of everything we see today. Scientists have argued about the CMB for decades. Some thought the variations might be errors in the instruments. Others thought they might come from dust or other things in our own galaxy. But mission after mission has confirmed the same picture. The cosmic microwave background is real. The tiny variations are real. And they tell us exactly how the universe began its journey from a smooth fog to the complex web of galaxies we see today. Now we enter a strange and quiet time in the story of the universe. Scientists call it the Dark Ages. Not because anything bad happened, but because there was simply no light to see by. After recombination, the universe was filled with neutral hydrogen and helium gas. Just atoms floating in the darkness. No stars had formed yet. No galaxies existed. The only light was the fading glow of the CMB, and that was already shifting to wavelengths our eyes cannot see. Imagine floating in space during this time. You would see nothing, complete blackness in every direction, no stars to navigate by, no distant galaxies to wonder about, just you, alone in a universe filled with invisible gas. This darkness lasted for hundreds of millions of years, but something important was happening in that darkness. Something you could not see even if you were there. Gravity was at work. Remember those tiny variations in the CMB? Those spots where matter was just a little bit denser? Gravity was slowly pulling more matter toward those spots. The denser areas were getting denser. The emptier areas were getting emptier. It was a slow process, incredibly slow by human standards, but the universe had plenty of time. Here is where dark matter enters the story in a big way, and this is the part that changes everything we thought we knew about how the universe works. For a long time, scientists thought the universe was simple. There was matter, the stuff made of atoms that we can see and touch, and there was empty space. That was it. But then astronomers started noticing something strange. In the 1930s, a scientist named Fritz Zwicky was studying clusters of galaxies. These are huge groups of galaxies held together by gravity. Zwicky measured how fast the galaxies were moving and tried to figure out how much matter must be holding them together. The numbers did not add up. The galaxies were moving too fast. Based on the matter he could see, they should have flown apart long ago. Zwicky proposed that there must be some kind of invisible matter adding extra gravity. He called it dark matter, but most scientists did not believe him. The idea seemed too strange. Then, in the 1970s, an astronomer named Vera Rubin made an even more puzzling discovery. She was studying how spiral galaxies rotate. The stars at the edges of galaxies were moving just as fast as the stars near the center. This made no sense. Based on the visible matter, the outer stars should have been moving much slower. It would be like the outer planets in our solar system orbiting as fast as the inner ones. That would violate everything we know about gravity, unless there was more matter than we could see. A lot more matter. Rubin calculated that galaxies must be surrounded by huge halos of invisible stuff. Stuff that does not shine, stuff that does not block light, but stuff that has gravity and pulls on everything around it. Today, we know that dark matter makes up about 27% of the universe. Regular matter, the kind that makes up stars and planets and people, is only about 5%. The rest is something even stranger called dark energy. But that is another story for another time. The key point is this: dark matter was there from the beginning. It was created in the Big Bang along with everything else. And because dark matter does not interact with light, it started clumping together even before regular matter could. Think about what this means. During the Dark Ages, while regular hydrogen and helium gas was still too hot to collapse under its own gravity, dark matter was already building structures. Dark matter particles were pulling together into clumps. Small clumps merged to make bigger clumps. Bigger clumps merged to make even bigger ones. Dark matter created the scaffolding of the universe. It built the framework that regular matter would later follow. Without dark matter, the tiny variations in the early universe would not have grown fast enough. Regular matter alone could not have pulled together quickly enough to form stars and galaxies in the time we know they formed. This is why we call dark matter the great architect. It designed the structure of everything we see. The web of galaxies that stretches across the universe follows the pattern laid down by dark matter billions of years ago. Every galaxy sits inside a halo of dark matter that pulled it together in the first place. We cannot see dark matter directly. We have never held a piece of it in our hands. We do not even know exactly what it is made of. Scientists have proposed many possibilities: strange particles left over from the Big Bang, new types of matter that we have not discovered yet. Some have even wondered if our understanding of gravity might be wrong. But whatever dark matter is, its effects are undeniable. We see its gravity bending light from distant galaxies. We see its influence in how galaxies rotate and how clusters hold together. The math only works if dark matter is real. And during the dark ages of the universe, dark matter was busy building the stage for the next act of the cosmic story. The darkness could not last forever. Gravity was pulling matter together. Dark matter halos were growing, and inside those halos, regular matter was falling inward, getting denser and hotter. Eventually, somewhere in the universe, the first pocket of gas got dense enough and hot enough to do something amazing. It ignited. Nuclear fusion began. Hydrogen atoms started smashing together with enough force to fuse into helium. And when that happened, light burst forth for the first time since recombination. The first star was born. We do not know exactly when this happened. Our best estimates say it was somewhere between 100 million and 200 million years after the Big Bang. We do not know exactly where it happened. It could have been anywhere in the observable universe. We do not even know if it was a single star or many stars lighting up at nearly the same time. But we do know what these first stars were like, and they were nothing like our sun. Scientists call them population. 3 stars. This is a confusing naming system that goes backward. Population 1 stars are the youngest, like our sun. Population 2 stars are older. And population 3 stars are the oldest of all, the very first generation. These first stars were giants, monsters compared to anything we see today. They could have been hundreds of times more massive than our sun. Some might have been 1,000 times more massive, and their surfaces would have been incredibly hot, glowing with intense blue-white light. Why were they so big? Because of what they were made of. Remember, the Big Bang only made hydrogen and helium. No heavier elements existed yet. No carbon, no oxygen, no iron, nothing but the 2 lightest elements. It turns out that heavier elements help gas cool down as it collapses. They act like radiators, letting energy escape. But the first gas clouds had no heavy elements. They could not cool as efficiently, so they had to get much denser and much more massive before they could collapse into stars. The result was stars that burned incredibly hot and incredibly fast. A star like our sun will shine for about 10 billion years. But those first massive stars burned through their fuel in just a few million years. Some of them lasted only a million years or even less. That is a blink of an eye in cosmic terms. And when those first stars died, they died in spectacular fashion. Stars that massive do not fade away quietly. They explode as supernovas, giant blasts that outshine entire galaxies for a few weeks. Or they collapse directly into black holes, swallowing most of their matter in an instant. These explosions changed everything. For the first time, heavy elements were created. The intense heat and pressure of a supernova can fuse atoms together to make things like carbon, oxygen, silicon, and iron. Elements that are essential for planets. Elements that are essential for life. The first generation of stars seeded the universe with new materials. They scattered heavy elements into the surrounding gas. And when the next generation of stars formed from that enriched gas, they were different. They could be smaller, they could burn longer, they could have planets made of rock and metal instead of just gas. But the first stars did something else too, something even more dramatic. They ended the Dark Ages permanently. Massive stars put out enormous amounts of ultraviolet light. This is light with so much energy that it can knock electrons right off atoms. When that happens, we say the atom has been ionized. It is no longer neutral. The first stars sent waves of ionizing radiation out into the universe. Slowly, the neutral hydrogen gas that had filled space since recombination started to break apart. Electrons were stripped away. The universe began to glow again, not with the old light of the CMB, but with new light from these first stars. We call this period reionization. It took a long time, hundreds of millions of years. Different parts of the universe were reionized at different times. Bubbles of ionized gas grew around each star or group of stars. These bubbles expanded and merged. Eventually, the whole universe was reionized. By about 1 billion years after the Big Bang, the Dark Ages were completely over. The universe was filled with stars. Light could travel freely again, and the first galaxies were taking shape. Those first galaxies looked nothing like the beautiful spirals we see pictures of today. They were small. They were chaotic. They were messy blobs of stars and gas crashing into each other and merging constantly. Remember the dark matter halos we talked about? Regular matter fell into those halos and collected at the centers. The first galaxies formed where the dark matter was densest. They were guided by the invisible framework that dark matter had built during the Dark Ages. These early galaxies were like construction sites. Stars were forming at incredible rates, much faster than stars form in modern galaxies. The gas was thick and turbulent. Collisions and mergers were common. It was a violent and energetic time. But from this chaos, order began to emerge. Small. Galaxies merged to form bigger ones. The biggest dark matter halos attracted the most matter and grew the fastest. Over hundreds of millions of years, the tiny blobs became recognizable shapes. The process of galaxy building is called hierarchical structure formation. That is a fancy way of saying that big things are made by combining smaller things. It is like building with blocks. You start with tiny pieces, you stick them together to make bigger pieces. You stick those together to make even bigger ones, and eventually you have something impressive. Dark matter led the way in this building process. Dark matter halos formed first. They created the gravitational wells that pulled in regular matter. Small halos merged to form larger halos. And as the halos merged, the galaxies inside them merged too. Picture two small galaxies approaching each other. Each one sits inside its own dark matter halo. The halos start to feel each other's gravity. They fall toward each other. The galaxies inside follow along for the ride. When the halos merge, the galaxies crash together. Galaxy mergers are not like car crashes. They are slow and drawn out. Remember, we are talking about objects that are thousands of light years across. Even moving at hundreds of kilometers per second, it takes millions of years for two galaxies to fully combine. And during that time, incredible things happen. Stars rarely collide with each other during galaxy mergers. Space is so empty that two stars hitting directly would be extremely unlikely. But the gravitational forces twist and pull everything around. Stars get flung onto new orbits. Gas clouds compress and trigger bursts of star formation, the shapes of both. Galaxies get distorted beyond recognition. Some galaxy mergers create long tails of stars stretching out into space. Some create rings or bridges of matter connecting the colliding systems. Some trigger such intense star formation that they glow incredibly bright with the light of millions of new stars being born at once. After hundreds of millions of years, the merger is complete. The two original galaxies are gone. In their place is a single larger galaxy, sitting inside a single larger dark matter halo. And this process repeats over and over throughout cosmic history. The early universe was especially violent. Galaxies were closer together because the universe was smaller. Mergers happened constantly. Many galaxies went through dozens of major collisions in their first billion years of existence. But here is something fascinating. Despite all this chaos, certain patterns emerged. Some galaxies ended up as flat spinning disks with spiral arms. Others became round balls of stars with no particular structure. How does chaos lead to such different outcomes? The answer lies in how the mergers happened and how much gas was involved. When two galaxies of similar size collide head-on, the result is usually a round elliptical galaxy. The collision scrambles all the orderly rotation. Stars end up on random orbits going every which way. The final shape is a smooth blob with no disk and no spiral arms. But when a small galaxy falls into a much larger one, or when the galaxies brush past each other at an angle, things can turn out differently. The larger galaxy might keep most of its structure. It might even gain new gas that settles into a disk and makes the spiral arms more prominent. Gas plays a huge role in this process. Unlike stars, gas can bump into itself. It can lose energy through friction and settle into a flat, rotating disk. If a lot of gas survives a merger, it will fall to the center and form a new disk. This disk can become the foundation for a beautiful spiral galaxy. Early galaxies were rich in gas. The universe had not yet converted most of its hydrogen into stars. So many of those first galaxies had the raw material to form disks after their merger settled down. Over billions of years, those disks developed spiral arms and took on the shapes we recognize today. Let us talk more about how spiral arms form. They are not solid objects. The stars in a spiral arm are not permanently stuck there. Instead, spiral arms are like waves moving through traffic on a highway. Imagine a stretch of road where cars slow down a bit because of a curve or a hill. Cars bunch up at that spot. But each individual car passes through and speeds up again on the other side. The slow spot stays in place, but the cars themselves keep moving through it. Spiral arms work the same way. They are density waves moving through the disk of a galaxy. Stars slow down a bit when they pass through the wave. This causes a traffic jam of stars, making that region brighter. But each star eventually speeds up and leaves the spiral arm, only to enter another one later in its orbit. These density waves also trigger new star formation. When gas clouds pass through a spiral arm, they get compressed. This compression can push the gas over the edge, causing it to collapse and form new stars. That is why spiral arms often glow with the blue light of young, hot stars. The stars that formed in the arm light it up, even as older stars are just passing through. Our own Milky Way has beautiful spiral arms. You can see evidence of them if you look at the band of light across the night sky. The brightest parts are where we are looking along a spiral arm, seeing more stars stacked up along our line of sight. But not all galaxies became spirals. Some ended up as ellipticals, and the biggest ellipticals are the most massive galaxies in the universe. Giant elliptical galaxies sit at the centers of galaxy clusters. These are huge collections of hundreds or thousands of galaxies, all bound together by gravity. The galaxy at the center has been there the longest. It has swallowed countless smaller galaxies over billions of years. Each merger added more stars and scrambled the structure more, leaving a massive round blob. These giant ellipticals can contain trillions of stars. They are surrounded by enormous dark matter halos that dwarf the halos of spiral galaxies. They are the ultimate winners in the cosmic game of merger and growth. But there is a price for getting so big. Giant ellipticals have very little gas left. They converted most of their gas into stars long ago, or they blew it away with the energy from all those starbursts and mergers. Without gas, they cannot make new stars. Their stars are old and red. No blue young stars light up their interiors. Spiral. Galaxies like our Milky Way are still making new stars. We still have gas in our disk. Every year, a few stars form in our galaxy. We are middle-aged in cosmic terms, still active, still growing a little, but past the wild days of our youth. Now let us zoom out and look at the biggest scales. Galaxies are not spread randomly through the universe. They are arranged in a pattern, a cosmic web of matter that stretches across all of space. Remember those tiny fluctuations in the cosmic microwave background? Those slightly denser spots in the early universe? They grew and grew under the influence of gravity. Dark matter pulled together into halos. Those halos merged into bigger halos, and the matter accumulated along certain paths and avoided others. The result is a universe that looks like a sponge or a foam. There are thin walls and long filaments of galaxies. These structures surround huge, empty voids where almost nothing exists. The filaments meet at nodes where galaxy clusters form. It is an enormous cosmic web, and dark matter is the thread that holds it together. We can see this structure when we map out where galaxies are located. Surveys that have measured the positions of millions of galaxies show the same pattern over and over. Filaments connecting clusters, walls surrounding voids. The universe is not random, it has structure at the largest scales we can see. Computer simulations can recreate this structure. Scientists program in the physics of dark matter and regular matter. They start with the tiny fluctuations we see in the CMB. And when they run the simulation forward in time, the dark matter naturally forms into a cosmic web. Regular matter follows along and forms galaxies in all the right places. The match between simulations and observations is remarkable. It gives us confidence that we understand the basic physics. Dark matter is really there. It really shaped the universe in the way we think it did. But there are still mysteries. The simulations predict certain things that we do not see, and they fail to predict certain things that we do see. Scientists are still working out the details. For example, the simulations predict that big galaxies like the Milky Way should have thousands of small satellite galaxies orbiting around them. But we only see a few dozen around the Milky Way. Where are the rest? Maybe they are there but too dim to see. Maybe some process destroyed them or prevented them from forming stars. This is called the missing satellites problem, and it remains an active area of research. There are also questions about what happens at the very centers of dark matter halos. The simulations predict that dark matter should be extremely dense at the center, but observations of some small galaxies suggest the dark matter is spread out more evenly. Scientists call this the core cusp problem. It might mean we are missing some physics in our simulations. Or it might mean we need to observe more carefully. These problems do not mean dark matter is wrong. The overall picture works far too well for that. But they do mean we still have more to learn. The story of the universe is not finished. We are still writing new chapters. Let us return to the story of individual galaxies and follow their journey through cosmic time. After the chaotic early days, galaxies settled into more regular patterns. Spiral galaxies spun steadily. Elliptical galaxies drifted through space. Star formation continued, though at a slower pace than before. The universe was about 3 to 4 billion years old when something interesting happened. Star formation across the entire universe reached its peak. More new stars were being born during this era than at any time before or since. Astronomers call this the cosmic noon. It was the high point of the universe's productivity. Why did star formation peak at this time? Several factors came together. The universe had enough heavy elements to cool gas efficiently and form stars easily. But the universe had not yet used up all its gas or heated it too much. Galaxy mergers were still common enough to trigger starbursts, but not so violent that they disrupted everything. After cosmic noon, star formation began to decline. The universe was running out of fresh gas. The gas that remained was getting hotter, heated by radiation from stars and from material falling into black holes. Hot gas cannot collapse easily. It resists the pull of gravity. By the time the universe was about 8 or 9 billion years old, most galaxies had settled into their mature forms. Spirals kept spinning, ellipticals kept sitting, new stars formed, but slowly. The wild days were over. Our own sun was born about 4.5 billion years ago, when the universe was already 9 billion years old. In cosmic terms, our sun is a latecomer. It formed from gas that had already been through several generations of stars. The heavy elements in the Earth, and in your body were forged in stars that lived and died long before our solar system existed. Think about that for a moment. The iron in your blood was made inside a massive star that exploded billions of years ago. The oxygen you breathe was created in the nuclear furnaces of stars that no longer exist. You are literally made of stardust. The story of the early universe is not ancient history. It is your personal history. It is the story of where you came from. Now let us look at galaxies in the present day and see how the early history still affects what we observe. The Milky Way is a typical spiral galaxy. It has a flat disk about 100,000 light years across. It has a central bulge of older stars. It has beautiful spiral, arms traced by young blue stars and glowing gas clouds. And it sits inside a dark matter halo that extends far beyond the visible stars. We can measure the rotation of the Milky Way very precisely. And the measurements confirm what Vera Rubin discovered decades ago. The outer parts of our galaxy are rotating faster than they should based on the visible matter alone. The dark matter halo provides the extra gravity needed to explain what we see. The Milky Way also has a supermassive black hole at its center. Almost every large galaxy has one. These black holes contain millions or even billions of times the mass of the Sun, all packed into a region smaller than our solar system. How did these supermassive black holes form? This is still an active question. Some scientists think they grew from the first stars. Remember those massive population 3 stars that collapsed into black holes? Maybe some of those black holes merged and grew and eventually became the monsters we see today. Others think there might have been a shortcut. Maybe some massive gas clouds in the early universe collapsed directly into black holes without ever becoming stars. These would have been big black holes from the start, giving them a head start on growth. We know that black holes grew rapidly during the early universe. When matter falls into a black hole, it heats up and glows intensely before crossing the event horizon. We call this an active galactic nucleus, or a quasar, if it is bright enough. The early universe was full of quasars. Black holes were eating matter at enormous rates. Today, most supermassive black holes are quiet. They are not eating much. The Milky Way's central black hole is currently dormant, but we can still measure its mass by watching stars orbit around it. And that mass tells us about the violent history of feeding and growth that happened long ago. The connection between galaxies and their central black holes is one of the most fascinating topics in modern astronomy. There is a tight relationship between the mass of the black hole and the properties of the surrounding galaxy. Bigger galaxies have bigger black holes. This correlation is too tight to be a coincidence. Somehow, the growth of the black hole and the growth of the galaxy are linked. They regulate each other. When the black hole eats a lot of matter and shines brightly, it can blow gas out of the galaxy. This stops star formation and prevents the galaxy from growing more. The black hole acts like a thermostat, keeping the galaxy from getting too big. This feedback loop is another area where our understanding is still developing. The basic idea makes sense, but getting the details right in simulations is hard. Scientists are constantly refining their models to match what we observe. Let us step back and think about what we have learned so far. The universe began in a hot, dense state. It expanded and cooled. The first atoms formed after about 380,000 years. Then came the Dark Ages, hundreds of millions of years when no stars shone. During the Dark Ages, dark matter was busy building the scaffolding of the universe. It pulled together into halos that would later host galaxies. Without dark matter, the small variations in the early universe would not have grown fast enough. Structure would not have formed in time. The first stars were massive and short-lived. They created heavy elements and rionized the universe. They ended the Dark Ages and lit up the cosmos for good. Galaxies formed inside dark matter halos. They grew through mergers. Some became spirals, some became ellipticals. The largest ones grew supermassive black holes at their centers. Over billions of years, galaxies settled into their current forms. Star formation peaked and then declined. The universe became the place we see today, full of mature galaxies arranged in a cosmic web of filaments and clusters. This is the tale of gravity and dark matter. Gravity is the force that pulls everything together. Dark matter provided the framework. Regular matter followed along and lit up the darkness with stars. The result is a universe of incredible beauty and complexity, all arising from simple beginnings and a few basic rules. But the story does not end here. The universe is still evolving. Galaxies are still merging, stars are still forming, though more slowly than before. And dark matter continues to shape the future just as it shaped the past. Let us look at what lies ahead. The Milky Way and our nearest large neighbor, the Andromeda Galaxy, are falling toward each other. In about 4 or 5 billion years, they will collide. It will be a slow collision, taking hundreds of millions of years to complete. But the result will be dramatic. Both galaxies will be transformed. Their spiral structures will be destroyed. Stars will be flung onto new orbits. The two supermassive black holes at their centers will eventually merge into an even larger one. The final result will probably be a giant elliptical galaxy, a blob of stars with no spiral arms. By that time, our sun will be nearing the end of its life. It will have swelled into a red giant, swallowing Mercury and Venus and baking the Earth. Life on Earth, if it still exists in any form, will face serious challenges. The merger with Andromeda will be the least of our worries. But think about what intelligent beings might see from some planet in that merged galaxy, billions of years in the future. They would look back at history and see the same story we have been telling. The Big Bang, the Dark Ages, the first stars, the formation of galaxies. They would trace their own origins back to the same cosmic processes. The story of the universe is universal. It applies everywhere and to every galaxy. The physics that shaped the Milky Way shaped every other galaxy too. Dark matter built the same kind of halos around every galaxy. Gravity followed the same rules everywhere. This universality is one of the most profound discoveries of modern science. The universe is comprehensible. The same laws that govern falling apples and orbiting planets also govern the formation of galaxies billions of light years away. We can understand it all with mathematics and physics, and dark matter, invisible as it is, fits perfectly into this framework. We cannot see it, we have never touched it, but we can calculate its effects with precision. We can predict where it should be and how much there should be. And when we check those predictions against observations, they match. Some people find it strange that we believe so strongly in something we cannot see. But think about all the things you believe in that you cannot see directly. You cannot see radio waves, but you trust that your phone works because of them. You cannot see atoms, but you trust that matter is made of them. You cannot see the past, but you trust that history happened. Dark matter is no different. We believe in it because the evidence is overwhelming. The rotation of galaxies, the motion of galaxy clusters, the pattern of the cosmic web, the tiny variations in the cosmic microwave background. All of these independent lines of evidence point to the same conclusion. Dark matter is real. It makes up most of the matter in the universe, and it shaped the cosmos we live in now. Let us bring this story to its climax. What is the ultimate lesson of the early universe and the birth of galaxies? It is this: complexity arises from simplicity, order emerges from chaos. The universe started as a uniform hot fog. It had no stars, no planets, no galaxies, no life, just smooth, hot gas expanding into nothingness. And yet, from that simple beginning, everything emerged. Tiny fluctuations grew into enormous structures. Simple particles combined into complex atoms. Stars formed and made heavy elements. Planets formed from those elements. And on at least one planet, life emerged and evolved until it could look up and wonder about its origins. All of this happened because of gravity and dark matter working together over billions of years. Gravity is patient. It never stops pulling. Given enough time, it can turn a smooth fog into a rich tapestry of galaxies. Dark matter helped by providing a head start. It began clumping before regular matter could. It built the framework that galaxies would later inhabit. Think of dark matter as the architect and gravity as the builder. The architect draws up the plans, the builder does the actual construction. Together, they created the universe. And here is the most amazing part. You can see this story for yourself. Every time you look at the night sky, you are looking back in time. Light travels at a finite speed. The light from distant stars and galaxies has been traveling for years, centuries, or even billions of years before reaching your eyes. When you look at the Andromeda Galaxy, you are seeing it as it was 2.5 million years ago, when the Hubble Space telescope photographs distant galaxy clusters. It is seeing them as they were billions of years ago. We can literally watch the history of the universe unfolding across the sky. The most distant objects we have ever seen are galaxies from just a few 100 million years after the Big Bang. We are seeing them as they were during the era of the first stars. They are small and irregular, just beginning their journey of growth and transformation. They look nothing like the mature galaxies of the present day. But they are the ancestors of those modern galaxies. They are seeing our past. The James Webb Space Telescope is now showing us even more of this early universe. It can see an infrared light, which is perfect for catching the stretched and shifted light from the most distant objects. Every new image reveals more about the first galaxies and the first stars. The story of the early universe is still being written. What comes next in that story? Scientists have big questions they are still trying to answer. What exactly is dark matter? We know what it does, but not what it is made of. Experiments around the world are trying to detect dark matter particles directly. Underground detectors wait for the rare collision of a dark matter particle with a regular atom. So far, nothing has been found. But the search continues. Are there other forms of matter we have not discovered yet? Dark matter seems to come in one type. But maybe there are dark atoms, dark stars, dark chemistry happening in a shadow universe alongside our own. This sounds like science fiction, but it is a real possibility that scientists take seriously. How do galaxies and black holes grow together? The feedback loop between them is still not fully understood. New observations and better simulations will help us piece together this puzzle. What was the very first star like? We have never seen a population 3 star directly. They all died long ago. But maybe we will find their chemical fingerprints in the oldest stars that still survive. Or maybe new telescopes will let us see the light from their explosions still traveling through space after billions of years. These questions drive modern astronomy forward. Each answer reveals new mysteries. The story of the universe is far from finished. But one thing is certain, whatever we discover, gravity and dark matter will be at the center of the story. They are the two main characters in the cosmic drama. Gravity provides the action. Dark matter sets the stage. Together, they created everything we see. And that brings us to the final thought of this journey. You are part of this story, not just as an observer, but as a participant. The atoms in your body were made inside stars. The stars formed inside galaxies. The galaxies grew inside dark matter halos. And the halos grew from tiny fluctuations in the first moments after the Big Bang. Every atom of carbon in your cells was once floating in the core of a massive star. Every atom of oxygen you breathe was once blasted out in a supernova explosion. Every atom of iron in your blood was forged in temperatures hotter than the surface of the sun. The universe made you, not consciously, not deliberately, but through the patient work of gravity and dark matter over billions of years. You are the universe looking at itself and asking how it came to be. When you look up at the night sky, you are not looking at something separate from yourself. You are looking at your own extended family. Every star is a cousin. Every galaxy is a distant relative. We are all made of the same stuff, following the same rules, part of the same grand cosmic story. The early universe and the birth of galaxies. A tale of gravity and dark matter. This is your story. This is where you came from. And now you know how it all began. So the next time you find yourself outside on a clear night, take a moment to look up. Find the band of the Milky Way stretching across the sky. Look for the faint smudge of the Andromeda Galaxy if you know where to find it. Think about the light traveling across millions and billions of years to reach your eyes. And remember what you have learned here. You are seeing the handiwork of gravity and dark matter. You are seeing structures that began as tiny ripples in the primordial fog. You are seeing the result of billions of years of patient cosmic construction. The universe is vast. The timescales involved are almost impossible to comprehend. But the story is surprisingly simple at its heart. Gravity pulls things together. Dark matter gives it a head start. Stars shine, elements are made, galaxies form. And eventually, someone comes along to wonder about it all. That someone is you. And now you know the answer. At least you know as much as we currently understand. There will always be more to learn, more questions to ask, more mysteries to solve. But the basic story is clear. From nothing or close to nothing, the universe built itself. It did so using the simplest possible tools. Just gravity pulling matter together. Just dark matter providing invisible scaffolding. The rest followed naturally. This is perhaps the most profound message of all. The universe is creative. Given enough time and the right conditions, complexity emerges on its own. Stars form, galaxies take shape, planets are born, life evolves, minds develop that can ask questions about the cosmos. We are the universe understanding itself. We are atoms arranged in such a way that they can contemplate other atoms. We are the way the cosmos asks questions about its own existence. And that is an incredible thing to be. So thank you for joining me on this journey through the early universe. We have traveled from the hot fog of the Big Bang to the mature galaxies of the present day. We have met dark matter, the invisible architect. We have watched gravity do its patient work over billions of years. If this story captured your imagination, please let others know. Share this video with friends who might enjoy it. Leave a comment below with your thoughts. Did anything surprise you? Did anything challenge what you believed before? I would love to hear from you, and if you want to learn more about the cosmos, consider subscribing to this channel. There are always more stories to tell, more wonders to explore, more questions to answer. The universe is waiting. And now you know a little more about how it came to be. But before we part ways, let us take one more deep dive into some of the most fascinating details of this cosmic story. There are layers upon layers of wonder that we have only touched on briefly. Consider the scale of what we have been discussing. The observable universe is about 93 billion light years across. Light travels at 300,000 kilometers per second, and it would still take light 93 billion years to cross from one side to the other. That is a distance so vast that our minds simply cannot picture it properly. Within that volume, there are roughly 2 trillion galaxies. 2 trillion, that is 2 million million. And each of those galaxies contains somewhere between 100 million and a few trillion stars. The total number of stars in the observable universe is estimated at around 200 billion trillion. That is a 2 followed by 23 zeros. And here's the thing. Most of those stars probably have planets. Recent surveys suggest that planets are extremely common. Almost every star has at least one planet orbiting it. Many have several. The total number of planets in the observable universe might be even larger than the number of stars. Yet all of this, all 200 billion trillion stars and their planets and their moons and their asteroids and comets, all of this visible matter makes up only about 5% of the total energy content of the universe. Dark matter accounts for 27%. And the remaining 68% is something even more mysterious called dark energy. Dark energy is beyond the scope of what we have been discussing today, but it is worth mentioning because it shapes the ultimate fate of the universe. Dark energy is causing the expansion of the universe to accelerate. Distant galaxies are moving away from us faster and faster over time. In the far future, billions of years from now, this acceleration will isolate our local group of galaxies from everything else. Other galaxy clusters will have moved so far away and will be receding so fast that their light will never be able to reach us. The observable universe will shrink down to just our local neighborhood. Future astronomers, if there are any, will look out at a sky much emptier than ours. They will have no way of knowing about the cosmic web or the billions of distant galaxies. The evidence we use to understand the Big Bang and the early universe will have faded away. In a sense, we live in a special time, early enough to see the evidence of the Big Bang, late enough for complex life to have evolved. We can study the full history of the universe in a way that future generations may not be able to. Let us return to the story of dark matter and explore some of the strangest and most counterintuitive aspects of this mysterious substance. Dark matter does not interact with light. This is its defining feature. It does not absorb light, it does not emit light, it does not scatter light. Light passes right through it as if it were not there. But dark matter does interact with gravity. It has mass, it warps space and time just like regular matter does, and this warping of space is what allows us to detect it. When light from a distant galaxy passes near a clump of dark matter, the light bends. This is called gravitational lensing. Einstein predicted this effect over a century ago, and we observe it constantly in the modern universe. Sometimes the lensing creates beautiful arcs of light. Distant galaxies get smeared and stretched into curved shapes as their light passes through a massive galaxy cluster. By studying these arcs, astronomers can map out where the dark matter is located, even though they cannot see it directly. In some cases, the lensing creates multiple images of the same distant object. The light takes different paths around the dark matter, arriving at Earth at slightly different times and from slightly different angles. We see the same galaxy 2 or 3 or even 4 times arrayed around the foreground cluster like jewels around a crown. These observations confirm that dark matter is there. The visible matter in the clusters is not enough to create such strong lensing effects. Something invisible must be adding to the gravitational pull. Another way we detect dark matter is through the motions of galaxies and clusters. Remember Fritz Zwicky's original observation from the 1930s? He measured how fast galaxies were moving in a cluster and found they were going too fast to be held together by visible matter alone. Modern measurements confirm this over and over. Galaxy clusters are held together by dark matter. Without it, they would fly apart in a cosmic explosion of separating galaxies. We can also look for dark matter closer to home. The motions of stars in our own Milky Way tell us about the dark matter surrounding us. Stars in the halo of our galaxy, the sphere of old stars that surrounds the disk, are orbiting differently than they would if only visible matter were present. Some of these halo stars are on very elongated orbits. They plunge through the disk and swing out to great distances before falling back again. By tracking their paths precisely, astronomers can reconstruct the shape of the dark matter halo we live inside. It turns out our dark matter halo is not perfectly spherical. It is slightly squashed, somewhat like a football. It extends far beyond the visible stars, perhaps 10 times farther. The dark matter we cannot see outweighs all the stars and gas and planets in our galaxy by a factor of 5 or more. You are surrounded by dark matter right now. Not in great quantities because you are near the center of the galaxy where regular matter is also concentrated. But there is still plenty of dark matter passing through the room you're sitting in, through your body, through the Earth itself. It sounds strange to say that something is constantly passing through you without interacting, but remember, atoms are mostly empty space. The nucleus of an atom is tiny compared to the orbits of its electrons. And dark matter particles do not feel the electromagnetic force that would cause them to bounce off electrons or nuclei. A dark matter particle could travel straight through the entire Earth without hitting anything. It might interact gravitationally in a tiny way, but the effect would be far too small to notice. Dark matter is like a ghost passing through walls, except it is real and makes up most of the mass in the universe. Scientists have built elaborate experiments to try to catch dark matter interacting with regular matter. The idea is that once in a while, purely by random chance, a dark matter particle might bump into an atomic nucleus. These experiments use extremely pure materials, deep underground to shield from cosmic rays, cooled to near absolute zero to reduce background noise. So far, no definitive detection has been made, but the search continues. Every year, the experiments get more sensitive. Every year, we rule out more possibilities for what dark matter could be. The leading candidates for dark matter particles come from theories that extend our current understanding of physics. One popular idea involves particles called WIMPs, which stands for weakly interacting massive particles. These would be new particles not yet discovered, left over from the Big Bang. Another idea involves particles called axions, which are much lighter and would behave like waves more than particles. Experiments designed to detect axions use different techniques than those looking for WIMPs. There are also more exotic possibilities. Some scientists have proposed that dark matter might be primordial black holes, tiny black holes formed in the early universe. Others have wondered if dark matter might be made of particles that interact with themselves in complex ways, forming a kind of shadow world alongside our own. We do not know which of these ideas, if any, is correct, but we do know that some form of dark matter exists. The evidence is too strong to ignore. Whatever dark matter turns out to be, understanding it will revolutionize physics. Now let us explore another fascinating aspect of the early universe: The cosmic microwave background that we discussed earlier contains a wealth of information beyond just its temperature variations. The CMB also has a property called polarization. Light waves can vibrate in different directions. When electrons scatter light, they imprint a pattern of vibration on it. The CMB carries this pattern from the moment of recombination, like a fossil record of conditions in the early universe. By studying the polarization of the CMB, scientists can learn about the physics of the early universe in ways that temperature measurements alone cannot provide. One particularly exciting possibility is finding evidence of gravitational waves from the very first moments after the Big Bang. If the theory of cosmic inflation is correct, the rapid expansion of the early universe should have created ripples in space itself. These gravitational waves would have stretched and squeezed the fabric of the cosmos, leaving a very specific pattern in the CMB polarization. Finding this pattern would be extraordinary. It would confirm that inflation happened. It would tell us about physics at energy scales far beyond what any particle accelerator could ever reach. It would give us a window into the first fraction of a second after the Big Bang. Several experiments are searching for the signal. It is incredibly faint, and separating it from foreground contamination is challenging. There have been false alarms in the past, but scientists remain hopeful that a confirmed detection will come eventually. The CMB also tells us about the geometry of the universe. Is the universe flat like a sheet of paper? Or is it curved like the surface of a sphere or a saddle? The pattern of hot and cold spots in the CMB depends on the geometry. Remarkably, measurements show that the universe is flat to very high precision, not curved in any direction. This flatness is actually quite surprising. In most models of the universe, space would naturally be curved. Getting perfect flatness requires a special condition. Inflation explains this flatness. The rapid expansion stretched space so much that any initial curvature got smoothed out, just like the surface of a balloon looks flatter and flatter as you inflate it. The observed flatness of the universe is strong evidence that inflation really happened. Let us now consider the role of chance and necessity in the formation of galaxies and stars. The tiny fluctuations in the early universe were essentially random. They came from quantum effects, the inherent uncertainty at the smallest scales. A quantum fluctuation that happened to be a bit larger in one spot led to a denser region there. A fluctuation that happened to be negative led to an emptier region. These random fluctuations were then amplified by gravity into the structures we see today. The specific pattern of galaxies across the universe reflects those original random seeds. In a different universe, with different random fluctuations, the galaxies would be in different places. But while the details are random, the overall statistics are predictable. We can calculate how many fluctuations of each size there should have been. We can predict the average density of galaxies at different distances. We can compute how many large galaxies versus small galaxies should exist. This interplay of randomness and order is a deep theme in physics. The laws of nature are deterministic at the level of averages and statistics, but the specific outcomes, the particular arrangement of matter in our universe, involved randomness that we can never fully know or predict. Some philosophers find this mixture unsettling. They want either complete determinism or complete randomness. But nature gives us something in between. The universe is predictable in bulk, but unpredictable in detail. This has profound implications for questions about the origins of life and intelligence. The same random fluctuations that seeded the galaxies also determined where stars and planets would form. The specific circumstances that allowed life to arise on Earth depended on where particular atoms happened to end up after billions of years of cosmic evolution. We cannot calculate our way back to the initial conditions that produced us. We cannot predict whether life exists elsewhere in the universe just by knowing the laws of physics. The random component of cosmic history means there will always be aspects of existence that escape explanation. Yet the overall story is clear. Physics allows for life. The universe has the right properties for stars to burn steadily for billions of years, for heavy elements to form, for planets to exist in habitable zones, for chemistry to become biology. Whether this requires any special explanation or is just one possible outcome among many is a question philosophers still debate. Let us now return to the practical matter of how astronomers actually study the early universe. The primary tool is light. Telescopes collect light from distant objects and analyze it to learn about conditions in the past. The farther away an object is, the longer its light has been traveling and the farther back in time we are seeing. But there is a limit to how far back we can see with light. Before recombination, the universe was opaque. Light from that era was absorbed and re-emitted so many times that it carries no information about what things were like before. The CMB is the oldest light we can detect. It shows us the universe at an age of about 380,000 years. To learn about earlier times, we use other methods. The abundances of light elements like hydrogen, helium, and lithium tell us about conditions during nucleosynthesis just minutes after the Big Bang. The specific ratios of these elements match theoretical predictions beautifully, confirming our understanding of that early era. Gravitational waves offer another window. Unlike light, gravitational waves can pass through the opaque early universe without being absorbed. They carry information directly from the moment of their creation. The gravitational waves from inflation, if detected in the CMB polarization, would tell us about physics in the first tiny fraction of a second. Ground-based detectors like LIGO have already detected gravitational waves from merging black holes and neutron stars. Future space-based detectors will be sensitive to different frequencies and will probe different sources. Eventually, we may detect the primordial gravitational waves from the very beginning. Neutrinos also escape from the early universe. These are ghostly particles that barely interact with matter. The universe is filled with neutrinos left over from the Big Bang, just as it is filled with the photons of the CMB. But detecting these relic neutrinos is extraordinarily difficult because they interact so weakly. No one has succeeded yet, though experiments are trying. Each of these windows reveals something different about the early universe. Together, they give us a remarkably complete picture of cosmic history, and as technology improves, we will see even more. The James Webb Space Telescope, launched recently, is already revolutionizing our understanding of the early universe. Its infrared vision allows it to see galaxies at earlier times than any previous telescope. Images from Webb show galaxies that existed just a few 100 million years after the Big Bang, when the universe was only a few % of its current age. Some of these early galaxies are surprisingly massive and mature-looking. This has challenged some of our assumptions about how quickly galaxies can form and grow. Scientists are still working out whether these observations require new physics or just adjustments to existing models. Future telescopes will push even farther. The extremely large telescope being built in Chile will have a mirror nearly 40 meters across. It will be able to study individual stars in nearby galaxies and detect the atmospheres of planets around other stars. Eventually, it might even see the light from the very first stars, the population 3 giants we discussed earlier. Radio telescopes are also essential for studying the early universe. The square-kilometer array being built in Australia and South Africa will be the largest radio telescope ever constructed. It will map the neutral hydrogen that filled the universe during the Dark Ages and study how ionization unfolded across cosmic time. All of this technology, all of this human effort, is directed at answering a simple question. How did we get here? How did the universe go from a smooth fog to a rich tapestry of structure and complexity? The answer involves gravity and dark matter, as we have seen, but filling in the details requires enormous ingenuity and collaboration across generations of scientists. Let us reflect on what this cosmic perspective tells us about our place in the universe. We are small, incomprehensibly small compared to the scales of galaxies and the cosmic web. Our entire planet is a tiny speck orbiting an ordinary star in the suburbs of an average galaxy. From a cosmic viewpoint, we barely exist. But we are also significant in ways that transcend physical size. We are the part of the universe that knows about itself. We are the atoms that have arranged themselves to ask questions about other atoms. Whatever happens in the far future, whatever civilizations rise and fall on countless worlds, we have participated in the great project of cosmic understanding. The story of the early universe is not just about distant objects in ancient times, it is about us. We are made of the matter that came from those first stars. We think using neurons built from atoms forged in supernovas. Our very existence depends on the patient work of gravity and dark matter over billions of years. Understanding this story changes how we see ourselves. We are not separate from nature. We are nature becoming conscious of itself. We are the universe waking up and looking around. Some find this perspective humbling, others find it inspiring. Perhaps it is both. We are humbled by the vastness and age of the cosmos. We are inspired by the realization that we can understand so much of it. And there is still so much more to learn. Dark matter remains mysterious. The details of galaxy formation are still being worked out. The nature of dark energy is completely unknown. Inflation might be correct, or it might be replaced by something better. The ultimate fate of the universe is uncertain. These are not just academic questions. They touch on the deepest issues of existence. Where did everything come from? Why is there something rather than nothing? How did matter become mind? These questions drive us to explore, to experiment, to think. The early universe and the birth of galaxies, a tale of gravity and dark matter. This is the grandest story ever told, and we are privileged to know it. So once more, thank you for taking this journey through space and time. May you carry this cosmic perspective with you wherever you go. May you see the night sky differently now, knowing what lies behind those points of light. And may your curiosity never fade. The universe has many more secrets to reveal. And together, we will discover them. But wait. We have covered so much ground, yet there are still fascinating threads to explore. Let us take some time to dive deeper into specific aspects of this cosmic story that deserve more attention. Consider the first galaxies once more. We mentioned that they were small and chaotic, nothing like the elegant spirals and smooth ellipticals of today. But what were they really like? What would you see if you could travel back in time to visit one? The first galaxies were probably clumpy. Instead of having smooth distributions of stars, they had bright knots of intense star formation connected by wispy trails of gas. Some might have looked like strings of glowing beads. Others might have been almost shapeless blobs. These early galaxies were very blue. The color of a galaxy tells you about its stars. Old red giants give off reddish light. Young hot stars shine with blue or white light. Because the first galaxies were making stars at tremendous rates, they were dominated by young blue stars. The gas in these galaxies was turbulent. Powerful outflows from supernovas and stellar winds churned everything up. There were no neat spiral patterns yet, just chaotic swirls of gas and stars crashing together and merging constantly. Black holes were already forming in some of these early galaxies. We detect quasars at tremendous distances, meaning their light has been traveling for most of the age of the universe. Those quasars are powered by black holes eating matter at enormous rates. The black holes must have formed and grown very quickly in the early universe. How did black holes get so big so fast? This is still an open question. If they grew from ordinary stellar remnants, there barely seems to be enough time. Some scientists propose that supermassive black holes form through direct collapse of giant gas clouds. Others suggest that the first stellar black holes merged rapidly in dense environments. The truth might involve a combination of processes. The relationship between black holes and their host galaxies is one of the most intriguing puzzles in modern astronomy. Black holes are tiny compared to galaxies. The black hole at the center of our Milky Way has a mass of about 4 million suns. But the Milky Way contains hundreds of billions of stars. The black hole is less than 1/100th of 1% of the total. Yet somehow, the mass of the central black hole is tightly correlated with properties of the entire galaxy. Bigger galaxies have bigger black holes. Galaxies with more massive central bulges have more massive black holes. This relationship holds across many orders of magnitude, from small galaxies to giant ones. The connection is too tight to be coincidental. The black hole and the galaxy must grow together, regulating each other somehow. The current thinking is that feedback from the black hole plays a crucial role. When the black hole is actively eating matter, it releases enormous amounts of energy. This energy heats the surrounding gas and can even blow it out of the galaxy entirely. With less gas, the galaxy makes fewer stars. And with fewer stars falling toward the center, the black hole has less food. It becomes quieter. Then, over time, gas accumulates again. Star formation resumes. Some of that gas eventually reaches the black hole. The cycle repeats. This feedback loop keeps the black hole and the galaxy in balance. Neither can grow too big too fast. They constrain each other through a cosmic thermostat. Computer simulations that include this feedback produce galaxies that look much more realistic than simulations without it. Before scientists understood this process, their simulated galaxies were too big and had too many stars. Including black hole feedback solved many of these problems. But the details are still being refined. How exactly does the energy from the black hole couple to the surrounding gas? What fraction of the energy goes into heating versus pushing? How does the feedback depend on the specific circumstances of each galaxy? These questions drive ongoing research. Let us now explore the cosmic web in more detail. We mentioned that galaxies are arranged in filaments and walls surrounding empty voids. But what does this structure look like up close? Imagine zooming in on a filament of the cosmic web. You would see a long cylindrical region, perhaps 100 million light years across, and stretching for billions of light years. Inside this filament, galaxies are scattered like grains of sand on a beach. Some regions are denser than others. Galaxy groups and small clusters dot the filament like beads on a string. The filament is not empty between the galaxies. Hot gas fills the space, heated to millions of degrees by shock waves from structure formation. This gas is so diffuse that it does not glow brightly. But it contains a significant fraction of the ordinary matter in the universe. In fact, most of the regular matter in the universe is not in galaxies at all. It is in this hot, diffuse gas that fills the cosmic web. Galaxies are like islands in a vast ocean of plasma. The islands are bright and easy to see. The ocean is dark and hard to detect. But the ocean contains more water than the islands. Where filaments intersect, you find galaxy clusters. These are the largest gravitationally bound structures in the universe. A single galaxy cluster can contain thousands of galaxies, plus enormous amounts of hot gas, plus even more dark matter holding it all together. The center of a galaxy cluster is a remarkable place. Galaxies are packed close together by cosmic standards. Collisions and mergers are common. The most massive galaxy sits at the center, having cannibalized many of its neighbors over cosmic history. This central giant is usually a huge elliptical galaxy, bloated with the stars of its many victims. Galaxy clusters grow by pulling in more matter from the surrounding filaments. Gas flows along the filaments toward the cluster. Small galaxies fall in and get absorbed. The cluster gets bigger and bigger over time. But there is a limit to how big clusters can get. Remember dark energy, the mysterious force accelerating the expansion of the universe? As the expansion speeds up, matter gets pulled apart rather than together. Eventually, the expansion will overcome gravity on large scales. Clusters will stop growing and begin to drift apart. In the far future, the cosmic web will dissolve. Filaments will stretch and break. Clusters will become isolated islands in an expanding void. The universe will get lonelier and lonelier as cosmic time goes on, but that future is billions of years away. For now, we live in an era where the cosmic web is still growing and evolving. Structure formation continues. New galaxies are still being born, though more slowly than before. The universe is middle-aged, past its productive peak, but still very much alive. Let us consider what happens inside galaxies in more detail. We have talked about star formation and galaxy mergers. But there is rich physics happening at smaller scales too. Stars form inside giant molecular clouds. These are huge regions of cold, dense gas, held together by gravity and shielded from starlight by dust. Inside these clouds, the temperature can drop to just a few degrees above absolute zero. At such low temperatures, gas can condense into ever denser clumps. Eventually, a clump gets dense enough that gravity overcomes all other forces. It begins to collapse. As it falls inward, it heats up. The center gets hotter and hotter. After a few million years, the center is hot enough to ignite nuclear fusion. A new star is born. But the collapsing cloud does not form just one star. It fragments into many pieces. Each piece collapses on its own. The result is a whole cluster of new stars born together from the same parent cloud. Young star clusters are beautiful objects. They contain hundreds or thousands of stars, all roughly the same age, glowing with the blue light of youth. Over time, the cluster disperses, the stars drift apart and join the general population of the galaxy. But for a few million years, the cluster exists as a distinct object. Giant molecular clouds come in all sizes. The biggest ones can contain several million times the mass of the Sun. They can be hundreds of light years across. When these giants collapse, they produce spectacular bursts of star formation with thousands of new stars lighting up at once. Our galaxy currently has plenty of giant molecular clouds. The spiral arms are full of them. That is why spiral arms glow with the light of young blue stars. The gas in the arms gets compressed as it passes through the density wave. This compression triggers cloud collapse and star formation. Elliptical galaxies are different. They have very little gas left. Their molecular clouds were used up long ago or blown away by energetic events. Without fresh gas, they cannot make new stars. Their stellar populations are old and red. This difference in star formation history gives spirals and ellipticals their distinctive colors. Spirals are blue because they have young stars. Ellipticals are red because all their stars are old. The color tells you about the life story of the galaxy. Some galaxies are in between. They have some gas and are making some stars, but at low rates. These are often galaxies that are transitioning from one type to another. Maybe they just experienced a merger that used up most of their gas. Maybe they are being stripped by the hot gas in a galaxy cluster. Galaxy evolution is complex and depends on environment and history. Let us also consider the role of magnetic fields in the universe. We have focused on gravity and dark matter, but magnetic fields are everywhere too. Galaxies have magnetic fields that stretch across their entire disks. These fields are weak by everyday standards, about 1,000,000 times weaker than a refrigerator magnet. But they extend over vast distances and influence the behavior of charged particles throughout the galaxy. Cosmic rays are one consequence of galactic magnetic fields. These are particles accelerated to enormous energies by shockwaves from supernovas and other violent events. Once accelerated, they spiral along magnetic field lines. They can travel across the entire galaxy before escaping into intergalactic space. When cosmic rays hit the upper atmosphere of a planet, they produce showers of secondary particles. Some of these particles reach the ground. You are being hit by cosmic rays right now. They are part of the background radiation that has been bombarding Earth since its formation. The magnetic field of our galaxy also affects our view of the cosmos. Radio waves and some other forms of light get their polarization rotated as they pass through regions with magnetic fields. By measuring this rotation, astronomers can map the magnetic fields of distant galaxies. The origin of galactic magnetic fields is still debated. Some scientists think small seed fields were generated in the early universe and then amplified by the motion of gas in forming galaxies. Others think the fields might have been created later by processes inside galaxies themselves. Understanding magnetic field origins is an active area of research. Magnetic fields also play a role in star formation. As a molecular cloud collapses, its magnetic field gets compressed and strengthened. The field provides support against gravity, slowing the collapse. It also channels the flow of material onto the forming star. Young stars often have powerful magnetic activity. They have star spots like our Sun, but covering much more of their surfaces. They blast out flares and coronal mass ejections that make solar events look tame. This magnetic activity gradually calms down as the star ages. Our Sun's magnetic field affects us directly. Solar flares can disrupt communications and power grids. The solar wind interacts with Earth's magnetic field to produce auroras. Understanding the Sun's magnetism is crucial for predicting space weather and protecting our technology. Now let us consider a question that often comes up when discussing the early universe. If the Big Bang happened everywhere at once, what is at the center? The answer is that there is no center. This is one of the most counterintuitive aspects of modern cosmology. The Big Bang was not an explosion in space, it was an expansion of space itself. Every point in the universe can equally claim to be where the Big Bang happened. Think of the surface of a balloon as it inflates. As the balloon gets bigger, every point on the surface moves away from every other point. There is no special spot that is the center of the expansion. The center of the balloon is inside, in the three-dimensional space that the balloon surface does not occupy. The universe is similar, but in 3 dimensions. We are confined to the three-dimensional surface of something expanding in a higher dimensional sense. There is no special center within our three dimensions. This is related to the cosmological principle, the assumption that the universe looks roughly the same everywhere and in every direction. On large scales, this seems to be true. Galaxy clusters are distributed uniformly. The CMB is nearly the same temperature everywhere. There is no evidence for a special location or direction. If the universe had a center, we would expect to see something different when we look toward it versus away from it. We do not see this. The universe appears homogeneous and isotropic, the technical terms for same everywhere and same in all directions. This does not mean everything is identical everywhere. Local variations exist. Some regions are denser than others. But these variations are random and do not indicate a preferred center. The cosmic web has a complex structure, but that structure has no preferred location. Another common question is what existed before the Big Bang. This is tricky because the Big Bang marks the beginning of time as we know it. Asking what came before might be like asking what is north of the North Pole. The question assumes a framework that does not exist. Some theories propose that our Big Bang was part of a larger structure. Maybe our universe is one of many in a multiverse. Maybe it sprouted from the interior of a black hole in another universe. Maybe it resulted from a collision between higher dimensional objects called brains. These ideas are speculative and currently untestable. What we can say is that the standard Big Bang model describes the evolution of the universe from a very early time to the present very successfully. The predictions match observations with impressive accuracy. Whatever happened before, if there even was a before, the hot, dense early state that we call the Big Bang definitely occurred. Let us also address the question of what dark matter is not. Ruling out possibilities is part of how science progresses. Dark matter is not ordinary matter. That is just hard to see. We know how much ordinary matter was made in the Big Bang from the abundances of light elements. There's not enough ordinary matter to account for dark matter. Dark matter is not black holes, at least not predominantly. We would detect the gravitational effects of black holes differently than we detect dark matter. Searches for the microlensing that black holes would cause have ruled out most mass ranges. Dark matter is not dust or gas between stars. These would absorb and emit light in ways we do not observe. Dark matter is truly invisible across the entire electromagnetic spectrum. Dark matter probably is not neutrinos. Neutrinos do exist in huge numbers throughout the universe, but they move too fast to clump up properly. Dark matter that moves fast is called hot dark matter. The structure we see requires cold dark matter, meaning particles that were moving slowly when the universe was young. Cold dark matter particles would have been massive and slow. They would have started clumping early, building the halos that galaxies later inhabited. This picture matches observations well. The leading theoretical candidates are new particles not yet discovered by accelerators. Extensions of the standard model of particle physics often predict such particles. The search to detect them continues in laboratories around the world. Let us take a moment to appreciate how much we have learned in just the past few decades. In the 1960s, we did not know about the cosmic microwave background. We did not know about quasars or pulsars. We had only a rough idea of how old the universe was. The existence of other galaxies beyond our own had only been established 40 years earlier. In the 1980s, we could see the CMB but not its tiny fluctuations. We suspected dark matter existed but did not know how much. We had no direct evidence for black holes. The accelerating expansion of the universe was completely unknown. In the 2000s, we measured the CMB fluctuations precisely. We determined the composition of the universe, the mix of regular matter, and dark energy. We detected gravitational waves. We found thousands of planets around other stars. Today, we are imaging galaxies from the cosmic dawn. We are mapping the cosmic web in 3 dimensions. We are probing the physics of black holes with gravitational wave observations. We are searching for biosignatures on exoplanets. This progress is remarkable. Our grandparents lived in a time of profound cosmic ignorance. Our grandchildren will live in a time when many of today's mysteries are solved. We are fortunate to witness this ongoing revolution in understanding. But let us not become arrogant. The history of science is full of confident claims that turned out to be wrong. Dark matter might surprise us. The Big Bang model might need revision. Our current understanding, impressive as it is, remains provisional. This humility is appropriate for the scientific enterprise. We build the best models we can with the evidence we have. When new evidence arrives that conflicts with our models, we change the models. This willingness to be wrong and to update is what makes science different from mere belief. The story of the early universe and the birth of galaxies is our best current understanding. It may change in details or even in fundamental ways, but it represents the honest effort of thousands of people over decades to understand where we came from. And that effort continues every day in observatories and laboratories and offices around the world. Young scientists are starting their careers right now who will make discoveries we cannot imagine. The story has more chapters yet to be written. What role might you play in this ongoing story? Perhaps you will become a scientist yourself. Perhaps you will support science through your work or your taxes or your votes. Perhaps you will simply carry the wonder with you and share it with others. Whatever your path, you are now part of the community of people who know this cosmic story. You understand where the stars came from. You know why galaxies spin the way they do. You appreciate the invisible framework of dark matter that holds everything together. This knowledge is a gift. Pass it on. And now, truly, we have reached the end of our journey through the early universe and the birth of galaxies. This tale of gravity and dark matter spans 14 billion years and stretches across trillions of light years. It connects the smallest quantum fluctuations to the largest cosmic structures. It explains how simple beginnings led to the incredible complexity we see today. You are part of this story. Remember that when you look up at the night sky. Remember that the atoms in your body were made in stars. Remember that the structure holding those stars in place was built by invisible dark matter. Remember that gravity has been patiently working since the beginning of time to create everything you see. The universe is ancient and vast, but it is also knowable. Piece by piece, observation by observation, we are figuring it out, and that is perhaps the most wonderful thing of all. If you enjoyed this journey, please like this video and subscribe to the channel. Your support helps us make more content exploring the wonders of the cosmos. Leave a comment below sharing your thoughts or questions. What fascinated you most about this story? What would you like to learn more about? Thank you for spending this time with us. Until next time, keep looking up. The universe is waiting to share its secrets with those who ask. But before we truly part, let us linger just a bit longer on some remarkable details that enrich this cosmic story even further. Consider the element factories that stars represent. We mentioned that heavy elements are forged in stars and scattered by supernovas. But the process is more nuanced and beautiful than a simple summary can convey. Different elements are made in different ways. Hydrogen and helium came from the Big Bang. Lithium and some other light elements were also made then in tiny amounts. But everything heavier than helium was made later, inside stars. The cores of stars like our sun fuse hydrogen into helium. This is the main energy source for most of a star's life. Our sun has been doing this for about 4.5 billion years and will continue for another 5 billion or so. When a star exhausts the hydrogen in its core, things get interesting. The core contracts and heats up. Eventually, it gets hot enough to fuse helium into carbon and oxygen. For stars like our sun, this is the end of the line. The core becomes a white dwarf made of carbon and oxygen, while the outer layers drift away as a planetary nebula. More massive stars go further. After helium, they fuse carbon into neon, neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each stage happens faster than the one before. Hydrogen burning lasts millions of years. Silicon burning lasts just a few days. Iron is special. It is the most stable nucleus. Fusing iron does not release energy. Instead, it requires energy. When the core of a massive star becomes iron, fusion stops. Nothing holds the core up against gravity anymore. It collapses in a fraction of a second. The result is a supernova. The core becomes either a neutron star or a black hole. The outer layers are blasted into space at thousands of kilometers per second. And in the incredible heat and pressure of the explosion, elements heavier than iron are created. Gold, platinum, uranium, all the heavy elements you know, these are made in supernovas and in the mergers of neutron stars. They require conditions so extreme that only cosmic explosions can produce them. The gold in a wedding ring was forged in a catastrophic stellar death billions of years ago. This process is called nucleosynthesis, the making of new nuclei. Different sites produce different elements. Core collapse supernovas make certain things. Thermonuclear supernovas from exploding white dwarfs make others. Neutron star mergers seem to be especially important for the heaviest elements. We can trace the chemical history of our galaxy by studying the compositions of different stars. Old stars, formed when the galaxy was young, have very few heavy elements. They formed from gas that had only been enriched by a few generations of supernovas. Young stars, formed recently, have more heavy elements because more generations of stars have lived and died. Our Sun is a young star by this measure. It contains heavy elements that were made by many previous stellar generations. The planets and everything on them inherited this rich chemical mixture. We are the beneficiaries of billions of years of cosmic chemistry. Now let us discuss some of the peculiarities of cosmic time. When we look at distant galaxies, we are seeing them as they were in the past. A galaxy 10 billion light-years away appears as it was 10 billion years ago. But the galaxy has moved since then. Due to the expansion of the universe, that galaxy is now much farther away than 10 billion light-years. This leads to a confusing situation. The observable universe is about 46 billion light-years in radius, even though the universe is only about 14 billion years old. How can we see something 46 billion light-years away if light has only had 14 billion years to travel? The answer is that space itself has expanded since the light left that distant galaxy. The light has been traveling through expanding space. The galaxy was much closer when it emitted the light. By now, the expansion has carried it much farther away. This distinction between the distance light has traveled and the current distance to the source is important for understanding cosmic measurements. Astronomers have to account for expansion when interpreting observations. Another peculiarity is the relationship between redshift and time. When light travels through expanding space, its wavelength gets stretched. Blue light becomes redder. This is called cosmological redshift. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with redshift 2 means the universe was 3 times smaller when its light left. A galaxy with redshift 10 means the universe was 11 times smaller. The highest redshift galaxies we have seen have redshifts over 10, meaning we are seeing them when the universe was less than 1/10 of its current size. Converting redshift to time requires knowing how the expansion rate has changed over cosmic history. Dark matter slows expansion down through gravity. Dark energy speeds it up. Plugging in what we know about these components, we can calculate the age of the universe at each redshift. The cosmic microwave background has a redshift of about 1,100. It was emitted when the universe was about 380,000 years old, as we discussed. The earliest galaxies we have detected are from when the universe was only a few 100 million years old. Let us also consider the cosmic timescale from a different angle. If we compress the entire history of the universe into a single year, starting with the Big Bang at midnight on January 1st, what would the timeline look like? The Dark Ages would last until about January 14th. The first stars would ignite in mid-January. Our sun and solar system would form in early September. Life on Earth would appear in late September. Dinosaurs would roam in late December. Humans would arrive in the last few minutes of December 31st. All of recorded human history would fit in the last second of the year. This perspective shows how recent we are. The universe was doing interesting things for a very long time before we came along. Galaxies formed, merged, evolved, and reached their current states before Earth even existed. And the future stretches ahead just as vastly. The sun will continue shining for another 5 billion years. Some stars will burn for trillions of years. The universe itself may continue forever, getting emptier and colder but never ending. What will happen in that far future? Stars will gradually burn out. New stars will stop forming as galaxies run out of gas. The remaining stars will age and fade. Eventually, even the longest-lived red dwarfs will cool into dark cinders. Black holes will become the dominant objects in the universe. But even black holes are not eternal. Stephen Hawking showed that black holes slowly evaporate through a quantum process. Given enough time, even supermassive black holes will disappear in faint puffs of radiation. After the last black hole evaporates, the universe will be a cold, dark void filled only with lonely particles drifting through infinite space. This is the heat death of the universe, the ultimate fate predicted by thermodynamics. But this far future is so distant that the numbers are almost meaningless. The last black holes will not evaporate for a time span that makes the current age of the universe look like the blink of an eye. For all practical purposes, we do not need to worry about the heat death. What matters for us is the present era, the age of stars and galaxies. This is when complex structures can exist. This is when life can arise and thrive. This is the cosmological spring, the fertile period between the chaos of the early universe and the sterility of the far future. We are lucky to exist now. Or perhaps it is not luck. Perhaps conscious observers can only exist during this particular cosmic era. This idea is called the anthropic principle. It remains controversial, but it highlights the special nature of our current epoch. Let us end with some reflections on the human side of this cosmic story. The people who figured all this out were remarkable individuals. Albert Einstein, whose theories of relativity made modern cosmology possible. Edwin Hubble, who discovered the expansion of the universe. George Gamow and Ralph Alpher, who predicted the cosmic microwave background. Arno Penzias and Robert Wilson, who detected it accidentally while trying to calibrate a radio antenna. Vera Rubin and Fritz Zwicky, who found evidence for dark matter. Dozens of others who contributed essential pieces of the puzzle. These were people with limitations and flaws like all of us. They made mistakes. They had biases. They sometimes resisted new ideas that turned out to be correct. But through the collective process of science, testing ideas against observations and discarding what did not work, they built the understanding we have today. This is the power of science as a human institution. No individual scientist has to be perfect. The process of peer review, replication, and ongoing scrutiny catches errors over time. The result is knowledge that is far more reliable than any individual could achieve alone. You benefit from this collective effort every time you learn about the cosmos. The pictures from space telescopes, the explanations of how stars work, the maps of the cosmic web, all of this comes from generations of scientists building on each other's work, and the effort continues. Right now, someone is making an observation that will change our understanding. Someone is writing a paper that will solve a long-standing problem. Someone is having an insight that will open a new field of research. The story is not finished. Perhaps someday humans or our descendants will travel to other stars. Perhaps we will colonize other worlds. Perhaps we will meet other intelligent beings who have their own version of this cosmic story. Or perhaps we will remain confined to this small corner of the galaxy, learning what we can from afar. Whatever happens, the universe will continue on its majestic path. Stars will burn and die. Galaxies will collide and merge. Dark matter will silently guide the flow of matter on cosmic scales. The story of gravity and dark matter will keep unfolding for billions of years to come. And somewhere in that vast expanse of space and time, there might be others like us looking up at their own night sky, wondering where it all came from. They would find the same physics, the same story, the same tale of gravity and dark matter shaping the cosmos. This universality is perhaps the deepest truth of all. The universe follows the same rules everywhere. The same story plays out around every star, in every galaxy, across all of space. We are connected to everything not just by shared origins, but by shared physics. The laws that govern the motion of electrons around atoms also govern the motion of galaxies through the cosmic web. In understanding this story, you have joined a community of beings throughout the universe who have looked up and asked how it all works. You have participated in the grand project of cosmic understanding. You have become the universe knowing itself. What a remarkable thing to be. So with that final thought, we conclude our exploration of the early universe and the birth of galaxies. This tale of gravity and dark matter has taken us from the first moments after the Big Bang to the present day and beyond into the far future. Remember what you have learned here. Share it with others. Let the cosmic perspective enrich your view of everyday life. and never stop asking questions about the wonderful universe we inhabit. If you found value in this video, please like, subscribe, and share with friends who might enjoy it. Your support makes more content like this possible. Leave a comment below with your thoughts. I read everyone and love hearing from you. Thank you for joining this cosmic journey. May your curiosity lead you to ever greater understanding. And may the wonder of the universe always inspire you. Take care, and we will see you next time. And one more thing before we truly say goodbye. Let us take a moment to address a question that many people ask when they first learn about the cosmic story. Why does any of this matter? Why should we care about events that happened billions of years ago, so far away that we can never visit them? There are many answers to this question, and different people find different ones compelling. Some care because of pure curiosity. The universe is there, vast and mysterious, and we want to understand it. This drive to explore and explain is deeply human. Our ancestors looked up at the stars and invented stories to make sense of what they saw. We are doing the same thing, just with better tools and stricter standards of evidence. Some care because the cosmic perspective changes how we see ourselves. Learning that we are made of stardust, that we exist on one small planet among trillions, that our entire species occupies less than a second of cosmic time, this knowledge is humbling. It puts our daily worries in perspective. It reminds us of what we share with all other living things. Some care because science works. The same methods that revealed the story of the early universe also gave us computers, medicine, agriculture, and all the technology that supports modern life. When we invest in understanding the cosmos, we develop techniques and train people who go on to solve practical problems. The skills transfer. Some care because the story is beautiful. There is genuine aesthetic pleasure in learning how things fit together. The way gravity and dark matter cooperate to build structure. The way stars seed the universe with heavy elements. The way tiny quantum fluctuations grow into vast cosmic webs. These patterns are elegant and satisfying. And some care because the alternative is ignorance. We live in a universe governed by physical law. Those laws operate whether we understand them or not. But when we understand them, we gain power over our circumstances. Knowledge is always better than ignorance. Whatever your reason for caring, the cosmic story rewards attention. Every new piece of knowledge connects to others. Understanding begets understanding in a virtuous cycle. And this brings us to the final message of this entire journey. The universe does not care about us. It follows its physical laws without regard for human hopes and fears. Stars burn and explode. Galaxies collide. Black holes devour matter. None of this happens with us in mind. But we can care about the universe. We can appreciate its beauty. We can work to understand its workings. We can share what we learn with others. In doing so, we add something to existence that would not otherwise be there. We add meaning. Meaning does not float in from outside. It is created by minds that observe and interpret and value. We are those minds. By caring about the cosmos, by investing effort in understanding it, we make the universe meaningful. This is not a small thing. In a cosmos of trillions of galaxies, the emergence of beings who can understand what is going on may be rare. Whatever the answer, we have the privilege of participating in this cosmic awakening. The early universe was simple. Hot gas expanding into nothing, no structure, no complexity, no observers. Gravity and dark matter changed that. They built the scaffolding for galaxies. They enabled stars to form and planets to coalesce and life to arise. And here we are, at the end of a long chain of cosmic evolution, able to look back and trace the story of how we came to be. We are the universe understanding itself. We are atoms contemplating atoms. We are stardust become conscious. There is profound beauty in this realization. It connects us to everything that exists. It reminds us that we belong here, that we are not strangers in the cosmos, but native children of it. The same forces that move the stars move through us. So go out tonight if the sky is clear. Find a dark spot away from city lights. Let your eyes adjust to the darkness and look up. See the band of the Milky Way stretching across the sky. Know that you are looking at your own galaxy from the inside. Every star you see is a cousin, born from the same primordial gas that made the sun. Find the Andromeda Galaxy if you know where to look. It appears as a faint smudge in the constellation Andromeda. That smudge contains 1 trillion stars. Its light has been traveling for 2.5 million years to reach your eyes. Think about the dark matter surrounding you. It is there, even though you cannot see it. It fills the halo of our galaxy. It holds the cosmic web together. It made everything possible. And remember the story. The Big Bang, the Dark Ages, the first stars, the birth of galaxies, the tale of gravity and dark matter working together over billions of years to create the universe we inhabit. You know the story now. You are part of the community of people throughout history and across the world who have wondered about the cosmos and sought to understand it. You carry this knowledge with you. Share it generously. The universe has given us something precious in allowing us to understand it. The least we can do is pass that gift along. Thank you once more for joining this journey. May your nights be clear and your curiosity endless. Until next time.